Thank you, Joe, for introducing me. Good afternoon, ladies and gentlemen. My name is Noel Piñas, and I am here on behalf of the Power team, which consists of me and my fellow colleagues Matt McCarty and Chelsea Brown. Next slide, please. Before I go into details about how we designed the power subsystem, I'd like to give you all a refresher on the orbiter's nominal power requirements, the UPS's nominal power requirements, and the power requirements of the probe when it is collecting scientific data, as well as an explanation of the margins that we applied during our analysis. As you can see, here is a breakdown of the orbiter's nominal power requirements when it is in operation around Uranus. As you can see, the biggest power draw are the thermal-electric heaters, followed by the standby power of the Piñas, and then the computer. Below all the loads and their respective power requirements, we included the following margins: 5% end of life as required by the RFP, 5% line efficiencies. We determined the 5% by looking at the wire and harnessing team's work and determining that 5% is a reasonable value. Then we looked at the specifications of our power electronics, and 5% inefficiencies are also given in the specifications. And the 5% for the unknowns is determined by how much the power requirements have fluctuated from the different teams. Taking into account these margins and the power requirements, the orbiter draws 293.31 watts electric. If there are any other questions, I'm going to move on to the UPS's breakdown for nominal power. Okay, UPS's nominal breakdown. Again, the biggest power draw during nominal mode around Uranus is the electrical heaters, followed by one of the X-band tweeters in standby, followed by the computer. Utilizing similar margins, the power draw of the UPS is 99.4 watts nominally. Next slide, please. And now here is a breakdown of the probe's power requirements when it is collecting scientific information. As you can see, utilizing similar margins that we instituted on the orbiter and the UPS, the power draw of the orbiter when it is collecting scientific data is 79.45 watts electric over a time span of 1.6 hours. Next slide, please. Finally, before I go into the details of our power subsystem, I would like to tell you about the external requirements imposed on the power subsystem by the RFP. The first one, there has to be a minimum 5% end-of-life margin on our power requirements. In addition, we must compensate for two-cell failure. In addition to that, we made some assumptions when conducting our analysis, based on our knowledge and skill level at this time in our engineering career. The first one, that within reason, the customer can provide us with the nuclear material that we require. The second one, small modifications can be made to commercially available off-the-shelf components as we see fit.
I have a question.
Yes.
So if you're carrying your 5% end-of-life power margin, and that's one of your requirements, I would interpret that as a 0% margin to your requirement. Your requirement is to carry 5% end-of-life power.
Right.
So you have no margin to your requirement.
We added an extra 5% to the power requirements of all the hardware. And then we saw if the ASRGs can provide that power, taking into account the 5% end-of-life margin. I mean, 5%, yes, that margin.
Okay.
I don't know if I answered.
It's a little hard to find that in your charts. If you go back, you've shown me you're carrying your extra 5% end-of-life margin.
Right. That is based on the pre-margin total of all the hardware, and then multiplying that by 1.05.
Okay. You have a miscellaneous margin.
Right, for any unknowns.
Okay. I would be calling those contingencies, and I'd be looking for a margin against that, but it's a language thing.
Okay.
It's not really a language thing, there's a formulation to that, is that you really should put contingency on at the component or subsystem level, and then stack it all up, and you get all done, you put a margin on the bottom. Right. It's a big number.
We like that.
And that's really
Yeah.
Then you can identify specifically what what's going on at the component level, and then you also know from a reliability point of view, what's the whole system doing.
That's a good point. If you can list that as an action item.
I did that already, guys.
Yeah, you got another one over here.
Thank you, guys.
I've been told that there's an ANSI standard for actually.
AIAA standard.
AIAA standard for how you do budgets, and it'd be great if you guys found it and then complied with it.
It's really, it's pretty good for power, but the AIAA standard for margin on mass is it's really weird, so.
Well,
Moving on to the next slide, please. Now that we know that the orbiter and the UPS vehicles have nominal power requirements, we need to look at what sort of power source we can use to provide this power at Uranus. Of course, using primary batteries is out of the question, and that to carry the amount of energy over the operational lifespan of these vehicles is going to require a ridiculous amount of mass to be launched off the surface of the Earth. So then we looked at solar panels. Out at Uranus, solar panels have very bad power density, and that it requires a very large surface area to provide even nominal power. That left us with radioisotope power sources. We desire them in that they have constant power output. Their power output degrades at about 0.8% per year, and they have the best power density for deep space operations. On the slide to my right, you will see several models of radioisotope power sources that we traded. This includes the ASRGs, the MMRTGs, the multi-100-watt RTGs, and the GPHS RTG. We did not go with the GPHS RTG because we found they are just no longer being made. That left us with the first three models that I mentioned. We eventually went with the advanced Stirling radioisotope generator because it has the best power density, the best efficiency, which is good since plutonium is in very short supply on the Earth, and it has the lowest housing temperature, which provides us with the best integration into the spacecraft. Next slide, please. Now that we know we want to go with the ASRGs as the primary power source, and we know the nominal power requirements of the orbiter and the UPS, we found that we need a minimum of 3 ASRGs on the orbiter and 1 ASRG on the UPS. Since the ASRGs come in finite power outputs, the additional power above nominal provides an additional 7.4% of margin on the orbiter vehicle and an extra 12% on the UPS. Additional margin is beneficial, and that provides us more power to charge the batteries, more power for the unknowns, and with adequate power management, we can get away with 1 total ASRG failure. I don't know if I mentioned this before, the probe is a single-use vehicle, so it will not have an onboard generator. Rather, it will be provided by batteries and powered by its carrier vehicle prior to deployment at Uranus. Next slide, please.
Sorry, is there a life specification on the ASRG?
Yes, they are rated right now for 17 years. We acknowledge that the operational lifespan of the orbiter is 21 years, so we're going to have to re-qualify them for the 21. If integration and test can elaborate on that?
It's okay, they haven't been qualified for the 17, so I don't care if you qualify. So go ahead.
Okay. Next slide, please.
They haven't been qualified for 8.
Okay. We acknowledge that the orbiter and UPS vehicles are going to have above nominal power requirements when they are doing anything besides sitting around. So rather than add ASRGs like 11 like I initially had, we decided to supplement the ASRGs with secondary batteries. On the slide to my left, you will see several secondary batteries that we traded. This includes nickel-cadmium batteries, nickel-hydrogen batteries, nickel-metal hydride batteries, and the lithium-ion batteries. We eventually went with the lithium-ion batteries because it has the best combination of energy density, self-degradation, and operating temperature. In addition, they are relatively easier to maintain in that they do not have any memory effects. Since the probe is going to be powered by batteries, we also chose to utilize lithium-ion batteries as well for the probe. I know that there are other probes that have used primary batteries, but because of the long transit to Uranus and taking into account self-degradation of primary batteries, the primary batteries will have barely any energy when arrival at Uranus. So rather than taking into that account, we're just going to charge the batteries of the probe prior to deployment.
You said it doesn't have memory effects.
Lithium-ions, yes.
Right. Does that mean you're charging them and recharging them?
Okay.
Why would you care? I guess the question is, why do you care if that memory effect? It doesn't just charge once and leave.
Well, we want to minimize lifetime degradation. Based on my research, memory effects contribute to the degradation of batteries. And we want the operation of the power subsystem to be as simple as possible. So we want to put the lithium-ion batteries.
In the orbiter.
Right. Okay.
What were you? Okay.
All right. I was thinking about their uses secondary.
Okay. If there are any other questions, I will move on to the next slide. To size the secondary batteries, it was not enough to look at the supplemental energy requirements. Rather, we had to look at the entire concept of operations to make sure that there was adequate amount of time and in between energy-intensive phases. As you can see on the slide to my left, we identified radio science around Uranus as the most energy-intensive phase for the orbiter, particularly radio science, egress, and ingress. On the slide to my right, you will see analysis we conducted on the depth of discharges of lithium-ion batteries. We conducted this analysis using MATLAB code that we wrote that takes into account the power required over time, the ASRG power output over time, the effects of varying current draws, and as well as the margin and inefficiencies that I mentioned earlier. Utilizing 3 strings in parallel with 9 cells in series, we found that during radio science egress and ingress, the maximum DOD is 45.1%.
So any 2 cells, you're attempting against 2 cell failure.
Yes.
So if the cell fails short, or if it fails open, how do you accommodate?
Oh, if it fails open, we have bypass diodes for the cells.
Thank you.
Next slide, please. Conducting similar analysis for the UPS vehicle, we identified the Uranus flyby as the most energy-intensive phase for the UPS, particularly at the beginning when it is preparing the probe for deployment. As you can see to my right, during probe deployment, the batteries are discharged to 81.7%, especially since we are charging the probes and the probe's computer is on during this charging phase. And this also takes into account 2-cell failure. Although 81.7% seems excessive, we deem this acceptable in that this is only a one-time occurrence throughout the whole entire operational lifespan of the UPS.
What's the risk of getting past that?
I'm sorry?
What drives it all the way down to that level?
Oh, what drives it all the way down? That is when the probe's computer is on to monitor the state of charge of its own batteries, and the batteries of the orbiter or the respective vehicle of the probe is also using its own energy and putting it into the probe's batteries.
Okay, so what's the risk of it, of you going past that number?
What's the risk of it? The risk of it is if the probe's batteries are depleted farther than what is.
What's the chance that it happens?
I have not looked into that, and that's definitely an item we need to look into.
Yeah. Now you can go tell me the other things about stuff.
I'm sorry?
Now you can go tell me what happens when you go past that. When you go past the 87%.
Oh, okay. Well, right now we anticipated a 90% depth of discharge of the batteries during that 3-hour charge to get it ready. So if it is depleted farther than that, then the concept of operations will have to be changed prior to this to put in more battery charge time for the probe. Did I answer your question?
Sort of. My concern would be is you're getting them awfully far depleted.
I'm sorry?
You're getting them pretty well depleted. If you get them a little bit more depleted than you are, they're dead. You can't get to that.
Past the 80%? Okay.
Get them all the way down to discharge.
Well, this is also taking into account true self-failure, and it only goes down to 80. I haven't seen any scenarios within the concept operations to show that it will get down to 80%. Of course, there are some things that may happen in operations that we can't anticipate.
But that's why my concern was what happens if you get past 87. You're getting close to the point where you're going to run out.
Well, that's the case that we'll make sure that it doesn't just, it gets to that Later on, I'll mention that within the command and data handling system, the power control and distribution unit, we have the ability to monitor the charge of the battery. So it's going to be it's going to have to be
You've
something
got another source of
that
power, so you don't have to go down.
I'm sorry.
You've got another source of power, so you don't have to get down that far.
We also have the ASRGs. The ASRGs are supplementing the batteries.
Okay.
Right, so what he's spoken as, if you get down below minimum voltage, you can't get the batteries back in.
Yeah.
And
Then we'll have to make
so
sure.
as part of your protection system, the subsystem has to be designed from a fault point of view, that if you get down, start getting to that voltage level, then you quit drawing from the battery.
My concern was you're getting down too far in your design, and so you have almost no margin, of safety. Okay, so you gotta get more margin of safety in there.
Okay.
Because at the level you're getting to, you're running the risk of killing your mission just as you're about to start.
Okay, that's a good point because that's an action item.
That's kind of what I'm trying to say.
But I think you said this or you alluded to it, you could change your charging scenario to reduce that peak?
Yeah, prior to this, we can always allocate more time to charge the batteries. It doesn't have to be here. This is not set in stone. The concept of operation still does have some leeway, especially since we have times when the spacecraft is not doing anything prior to arrival at Uranus.
Okay, you're definitely getting an action item on that then. Since you can't do it.
Moving on.
Dave, are you doing that?
I'm busy writing.
Good.
Okay, and here is a load profile for the probe when it is woken up from its 70-day hibernation. On the slide to my right, you will see a DoD plot that we conducted for this load profile. I must point out that upon waking up the probe from its 70-day transit, the probe's batteries are already depleted close to 40%. This is because during the 70-day transit, a 0.06 watt timer is active to wake up the probe. At the end of the planned operational lifespan of the probe, with 2 strings in parallel with 9 cells in series, and taking into account a 2-cell failure, the DoD of the batteries are at 2.6%. That gives us some time, well, some more energy, to see if the probe can just keep on ticking before it implodes. Next slide, please. Now we need to connect these power sources to the electrical hardware in the spacecraft, so we looked at the Terma Modular Medium Power Control and Distribution Unit. We looked at this because it is highly modular, has heritage, and its relatively lower size and mass allows it to be the best option for all 3 vehicles. I must point out that on the orbiter there is a large amount of hardware that needs individual control. Therefore, and in addition to that, for reliability, we need to double up on the amount of cards, so there is a large amount of cards on the orbiter. According to, I must elaborate on what I meant by cards. Cards are the Terma Modular Medium PCDU basically consists of a backplane, which is like the motherboard on a computer to which cards are attached. And each of these cards are in charge of different aspects of power control and distribution. From power control, power distribution to powering the pyros, powering the heaters, and relaying data to the command and data handling system. Because we need a large amount of these cards on the orbiter, and according to Terma specifications, we can only put a maximum of 21 cards inside one box. We need 3 boxes on the orbiter. One is the main PCDU, one is a communications hub, and the other one is an ADCS and props box, with the main PCDU supplying power to the hubs. On the UPS and the probe, there is a relatively lower amount of hardware that needs individual control, so all these cards can fit into one box. Next slide, please. In addition to these power electronics that I mentioned, we also need DC-DC converters. This is because of the 28-volt bus of all the vehicles. We chose 28 volts because we found that most of the hardware on these vehicles can accept 28 volts. For the hardware that can't accept 28 volt, we included inline DC-DC converters. To account for the inefficiencies of these DC-DC converters, we added an extra 20% to the power requirements of these components. Where we got 20% was by looking at commercially available off-the-shelf DC-DC converters with voltage transformation capabilities similar to that which we require. And on the slide to my right, you will also see that we integrated shunts into the power subsystem. This is because the ASRGs do not have the capability to turn down their power output. if the spacecraft is not utilizing all this power, whether it be for the electrical loads or the heaters, this power has to be shunted away as thermal power into space.
Does it really have to be dissipated as thermal?
Well, we can also dissipate it as through the communication system.
I don't know enough about the generator. What happens if you short it?
I'm sorry?
What happens if you short the generator to the ground? Does it cause problems for it?
Well, it's not like you can, because it's either all of it or none of it. You can't have an intermediate area in between. As far as I know, you can't get like 90 watts out of it.
Okay, yeah, you need switching it. Okay.
Right. And in the event of a bus failure, which is what shorting is.
No, that's okay.
Okay. And next slide.
No problem. I'm just thinking in terms of the way we do with solar cells.
Okay. Oh yes, the shunting of solar cells. Okay. So in summary, here is the orbiter's functional block diagram, which displays all the components that I mentioned earlier. The 3 ASRGs, lithium-ion batteries, the shunt cells, the power electronics that are contained within such boxes. If there are no questions on this, I'll move on to the yeses.
Just have one question on the PCB.
Sure.
Earlier, I had a concern about the IEM module, where the computers are.
Oh, the integrated electronics module?
Yeah, so if the main power supply goes off there, it's PCB. Computers are all down. And that backup power supply is off. Who's turning it on? They were saying the PCB doesn't.
From what I've read on previous missions, if something like that occurs, then the power control and distribution unit has the ability to sense if that particular component has failed. If it has sensed that component has failed, then the command and data handling card within the PCBU then relays that information to the command and data handling system.
Command and data handling, it's the IEM itself is going to transmit it?
I'm sorry?
Where's
Oh,
this
no,
part?
there's a command and data handling card within the PCBU that can transmit data to the command and data handling subsystem. It's just an interface card that monitors the power
Okay.
being distributed through the power
You're
subsystem.
saying there is a code?
Yes. Yes, there is a command and data handling interface card in the PCBUs.
Which one? So there's the main PCB, so.
Right. Yeah,
So that
there's,
second block.
Yes,
That's what you're saying.
right, top second left.
Fairly important, okay, thank you.
No, they have a requirement for no single point failures except for tested structure, but your primary power harness is a single point failure.
I'm sorry.
Your primary power harness.
Oh, yes.
Sure, it's out. That's the end of it.
Are you talking about the wires connecting?
All the wires.
Oh, yes. Forgot to mention in my presentation that all the components have main and redundant lines coming out of them, and each of these lines are connected to a different power distribution card. So all the cards are redundant and all the lines are redundant.
All the ASRGs don't have a come together into a single harness.
I'm sorry?
All the ASRGs.
All the ASRGs come in on one single harness though.
Yeah, and that's a single point.
Oh, well, we conducted analysis into seeing what would happen if we lost an ASRG, and we found that we can modify our nominal power requirements to get away with 2 ASRGs.
What happens if the harness shorts? The main primary harness shorts. It's a single point failure.
Main primary harness. Can you help me out with that, Matt?
Is there a credible failure mode for it?
I'm sorry.
Is there a credible failure mode for what the gentleman was saying?
Every harness line is redundant.
Basically, you see where the 3 wires come together after ACUA, ACUB, ACUC, that node right there is what he's talking about.
It's not just a single node. It's actually 3 different lines. That can be misleading. It's not like everything is put into one line. Each of the ASRGs have their own dedicated line to a power input card and 3 separate power input cards.
So
Yeah, 3 harnesses.
It's not listed in there. There are actually 3 input cards that we.
In the box that says input.
Yes, there are 3 connected to a separate ASRG.
So there really is not a single primary harness.
Right.
Okay, I'm sorry, I misinterpreted your question.
And they're all
So
there.
but you're saying there isn't.
Okay. Primary harness meaning a primary connection one primary connection to the ASRGs. Is that how?
Yeah, between the ASRGs.
Okay, then there isn't just one singular one. Each of the ASRGs have their own input into the power
Typically
subsystem.
there is, and usually we feel it's a critical component, so it has special handling precautions in manufacturing because we recognize it as a single point failure. But I wasn't quite sure which way you're going to go with it, that's what I was going to ask.
Okay,
But he would like you to picture your diagram.
Yeah, because it's not accurate.
okay. Action item.
You're all on second.
Sorry?
You're all on second.
Yes, separate lines, separate connectors, separate cards for the separate ASRGs. Okay, moving on. If there are no other further questions. Okay, moving on to the UPS's power subsystem. Similar to the ASRG, just much simpler in that, to the orbiter, just much simpler that we only have one ASRG and all the power electronic cards can be put into one box. Any questions? Moving on to the Pro power system. Here's a functional block diagram of the Pro power system. All the power electronics cards can be put into one box, and it does not have an onboard generator like I earlier mentioned. Instead, any of the electrical power that the probe requires prior to deployment at Uranus is provided by the carrier vehicle.
All of these should be used the same architecture, same redundancy for cost, or the ones that go on the probe, and that's what I'm calling
It depends on our needs. All the cards are similar, it's just that we size the amount of cards based on how many components we needed. But as far as
I did say how big the PCBs are.
if there are any further questions, I would like to pass it off to my colleague, Nick Dominikovic, for the harnessing team.